So let's just theoretically go back, because we need to understand this stuff and why we're doing this. So if you really have done the most simple experiment that you can do with transcriptomics, and you really have just said, what's the difference between when I add something and when I don't, or what's the difference between A and B, then really you've got, and let's say imagine we have done that in 3 times, then all you've got is a relationship between A and B. That's the only thing that can happen. So in terms of what a gene can do, it can either go up or go down. It can be not expressed, or this expression might not have changed. It's a fairly simple thing. So if we'd taken Claire's data set and gone, what's the difference between A and B? Well, there's 2 things here. I've got very little correlation space. Okay, if you're looking at a set of samples and they're all pretty well replicated, then essentially most things haven't changed. Okay, so most things are going to be correlated. So you put this graph, so you put this data into biolayout, and first of all you'll notice that at even the highest correlation setting, 0.99, there's a gazillion relationships. Okay, and that is because there's no real correlation space. Things are just, this is going to be correlated, okay, and everything, because you've got 20,000 measurements that look like that, they're all going to be correlated with each other, and therefore when you look at that correlation cutting, it's going to be there. So if you do manage to get it to that point, and then you make this cutoff, then what all you'll get in biolayout will be 2 big clusters, those that went up and those that went down. And if you lowered that correlation, eventually that would merge with all those things that didn't change. So actually, there's no point. If you've done an experiment like this, just do a statistical cutoff and say, what am I going to believe that's changed between A and B across a given threshold? You know, there's only one answer. It went up significantly or it didn't. Okay? There's no more to say about that. So this is not the type of data you want to be putting in biolayout. But the point I'm trying to make here is that as you increase the number of samples that you're actually investigating, then the number of potential patterns that can be in your data increases. So if we look at only the 3rd case now, that we've added a 3rd thing in here, well, things can have gone up between A and B and down between A and B, as we saw earlier, but then they could have stayed the same in C. Or they could have stayed the same between A and B, but then gone down in C. They could be high in A and gone down in B and C, or they could have changed. So there's only we're still only looking at 5 potential patterns of things that can do. And again, if you're going to do this, 3 statistical tests, and you've got the answer to what you want to do in a kind of robust way, potentially. Where it becomes interesting is you start adding extra samples in. So by the time we get to 4 samples, there are 15 different potential relationships that you could experience within that data set. Okay, now that's a lot of things. So even with just 4 sample sets, so then you can get into this world where you do multiple statistical comparisons. Okay, and this is very common, that this is what people do. And what you end up getting is that you're really getting lists upon lists upon lists of things that have changed, because you've asked lots and lots of questions of it, because you kind of know that these are the things you're looking for. But the other thing is that in any kind of pairwise statistical test, you're going to get the same things coming up more than once, because these guys relative to these guys are coming up, but they're also going to be coming up in this relationship as well. So that actually what your statistical pairwise comparison doesn't give you is any resolution to this. Okay. Now, so this is when it starts getting complicated, even before samples where you've got 4 comparisons. The reason I got into this is that we were looking at a mouse tissue atlas where there were 61 different samples, and I had no way of dividing up all of the patterns which could potentially be occurring across 61 different samples, and I thought there had to be a better way. So when you get to this kind of relatively still simple level of complexity, there's a lot of things. The other thing to mention is this is assuming that all your replicates replicate. Okay? That's the number of patterns that you would get if all 3 of your replicates were really tight. If you assume that there's variation between that, then the number of patterns you can potentially have in a data set becomes astronomically large. Okay? So this is why you need to think about how am I going to look at that complexity and view things. And of course, the other thing about statistics is that you always group your samples together, even if there is quite a lot of variation between your samples. And sometimes it's good to know that replicate 2 didn't work. Okay, you might want to just throw it out rather than ruining all your statistical power. Okay. So the way, as I mentioned before, is that what we're going to do here is that what the biolayout has been optimized to do is to make this calculation, the Pearson correlation. So it's an intensity and sample order independent. It doesn't matter which way you order your samples, your Pearson correlation between 2 sets of numbers will always be the same. So whether you put the replicates first or whether you put the time points first, the relationship between any 2 sets of measurements will be the same. And the intensity independent, so you have genes which are expressed at low level, you have genes expressed at high level. As long as the pattern is the same, and the pattern is the important thing here, the relationship will be the same. So 2 things can be shifted apart in terms of the actual intensity by a log order, but as long as the pattern is the same, they'll be the same. Okay. So the more data you have, the more significant the correlation value, and Pearson is used by many things.